recording. So this time we're going to get into something called more advanced propositions. So I want to ask you a quick question about the theory of computing, I guess you could say. Is it useful if a computer can give you the answer? Okay, so now let's dig into that more deeply. Is it good if the computer can give you an answer without letting you ask it a question? So like if it just tells you what to do, but you never actually get to tell you what kind of answer you want, would that be a good computer or not? So like what if everybody had to do the same thing all the time? Like they all went to the computer and told them the same answer for everybody. Like, would that be a smart computer? It wouldn't be very smart, right? You have to be able to put input into it in order for it to be useful. Put input into a proposition. So how many of you done computer programming before? Have you written a function before in computer programming have you heard of something called returning a value? Yes. Okay, perfect. So that's good. How many of you have written JavaScript before, by the way? Have you learned the arrow function notation that's like this? Let's say x maps to like x times x. Have you heard that? Learned that notation? So like you'd say like you could even declare it as a variable, like variable function equals x maps x to x. Now this looks really weird if you have it like that, but that basically defines a function called f that takes input called x and returns x times x. So if I said like variable y equals f of 3, who can tell me what would y equal? Right, y would equal 9 at that point in time. Right. And by the way, this is a comment in JavaScript if you write a slash with a star and then a star with a slash at the end. You can also do a single line comment like this by doing double slashes at the front. Except the problem is that if you do single line comment and you try to like move all your like bump a bunch, like let's say move your if your code gets wrapped wrong, then a single line comment might accidentally comment out a bunch of stuff after it because it doesn't have an endpoint. It just comments all the way to whatever's end. So like if you've ever had code that somehow somebody messes it up and it wraps the code below it up onto the line above it, a single line comment can sometimes cause issues. But if you use the other kind of format of a comment in JavaScript, then it ends itself, so you don't have to worry about what happens if it gets wrapped the wrong way. That's just something you learn about if you like deal with emails and like code getting messed up by the white space getting messed up. All right, well, so now you know that there's function is something you can put things into, right? And it gives you a value back. So you can actually have propositions that are like functions. So if I said, so what was the letter that we used for a proposition before? Like the 4 common letters starts with the letter P, right? P and Q and stuff like that. Like that's why they say mind your P's and Q's, because in logic you had to think about P's and Q's. And then like P, Q, R, S, and you could even have T, or etc. Of course, pretty soon you get to X and Y and Z, which are used for like algebra problems. But it could be any letter for a proposition. It doesn't really matter. So if you have a more advanced proposition that has input into it, then they usually use a capital letter with it. I mean, you don't have to, like, it's really just your preference. In fact, there's really no standard, I don't think. So what if I just declare the proposition P of X and Y to be equal to the statement X is bigger than Y? Like that. So what if now there's not really, and this isn't computer language, so there's not really actually like this isn't code that you can like compile into a certain result. So let me just ask you this question. What's the truth value of P of 3, 4? Is that true or false? So think about it like this. you're replacing x with 3 and y with 4. So that means P of 3, 4 is the statement 3 is greater than 4. That is false. You're right. So that is false. False. How about the statement P of 4, 3?
True.
Yep, that's true. Correct. So now you know how to do more advanced propositions. So let me ask you a question. Is it true that P of AB implies that P of A plus 1 B? Is that a true or false implication? So let's get to a little bit more abstract logic with that. That's true because if P of A, this means if this is true, then this is true. So if this is true, this means, what does it mean? It means A is greater than B, right? Then if A is greater than B, what does this mean? This means that A plus 1 is greater than B. Well, if A is already greater than B, then definitely A plus 1 would still be greater than B, right? Yeah. So that's a true statement. By the way, well, actually, I should be more careful. I should have done a capital P. Sorry, my fault. Sometimes I just forget. By the way, most programming languages, I believe, are case sensitive. So, and I think math is also case sensitive. So I should have done a capital P instead of being lazy. All right. So P of AB does imply P of A plus 1B. Okay, let's have you introduce one of your own propositional functions like that. So can anybody think of a proposition that could depend on input values? Yeah, so what's a proposition about things that would have, so like this is a proposition x is greater than y, and it depends on two input values, x and y. So
A plus 6 plus 7.
A plus 6 equals 7.
I don't know, A plus 6, comma, B plus 7.
Okay, hold on. Let me go back to this. So that could be a function, I think, from what I'm hearing you say, but that wouldn't be a propositional function because it doesn't have a true and false value. It just has an output value. It like calculates two outputs from the input.
Oh, I meant that way. He said it's like, right?
So it's like A plus 7 and B, you said?
Yes.
Okay, but okay, yeah, so it could calculate A plus 7 and could calculate B, like as two output values, but it needs to be something that's either true or false, though. So like you could say A plus 7 equals B, you could say. So like you could say P of XY is a statement that, and you can say A and B, that's totally fine. You can call it, just like computer programming, you can call the variables anything that you want to. In fact, math is basically really just computer programming with a little bit more, like hundreds of years of like expertise added on into it. So P of A and B, you said that P of A plus 7, and you just said return and B, right? So that'd be like two output values, like a vector of two things. Well, that's not a true and false value though, but what if I change that into something like this? That the output value of P of A and B was that A plus 7 equals B. How about that? Now, by the way, in computer programming, a lot of times the word equals is referred to an assignment. It just stores the value on the right side into the variable on the left side. So it's not a logical equals, it's just a storing operation. So in computer programming, a lot of times they use double equals or even triple equals to represent the logical equals. Like if A plus 7 logically equals B, they would put two equal signs between it. But we're just in a math class, so we're just going to use a regular equals. Sometimes actually computer programming is sometimes actually, I feel, more precise than even math is because of how you have to use specific notation exactly for everything in computer programming. So A plus 7 equals B. That's the truth value of a P of A and B. So can anybody give me an example of P of A and B where it would be false? So give me two numbers so the P of those two numbers would be false. 4 and 19, yeah. So P of 4 and 19 is the statement that 4 plus 7 equals 19, right? That's what it means. And that is false. So good job. Now give me two numbers so that P, the proposition P of those other two numbers would be a true statement. 1 and 8, right? So P of 1/8 represents the output statement is 1 plus 7 equals 8, and that's a true result. So these propositions' truth values depend on what you put into them. Just like the weather depends on what day it is. For example, like if you said, is it raining today? It might say no, or it might say yes, I don't even know what the weather is today. But if you said it's raining like next week, it might say the opposite. So propositions that depend on input are like more complex propositions. Now let's learn about something called quantifiers, and let's also learn a little bit more about negating things. Negating things is really hard, especially once you get to quantifiers. So some propositions are true for all things, are true always. So for example, if I said that if I said that, okay, here's an algebra problem. Tell me if you remember, who remembers this algebra problem? Sum from 1 through n is equal to n times n plus 1 divided by 2. Who remembers that? No, that's actually the last chapter of college algebra.
Okay.
Because that's an arithmetic series. The first term of it would be 1. The last term of it would be n. If you average the total of n and 1, you get n plus 1 divided by 2. That's the average of the first and last terms. And the number of terms being added is n. So this right here represents the average. If you cover up to n, this represents the average of the first and last value of the arithmetic sequence. If you take the average value of the whole sequence, multiplied by the number of terms in the sequence, which there's n terms in it, you get the total of it. So that's true. So this would be a proposition that says, so this would be a proposition depending on n, right? Proposition of n would be defined as, whoops, I forgot the most important part. I forgot the letter I. So the sum of each number called I, so you have to put the I inside of it. The sum of each number called I from I equals 1 through I equals n is equal to that. And that's a statement about the total of the first n numbers. So proposition number 1 means that the sum of the number 1 equals 1 times 1 plus 1 over 2. Is that a true statement?
Yeah.
And the proposition number 2 means the sum of the numbers 1 plus 2 equals, or well, we don't really need to write the sum in front of it, but that means the sum of the numbers 1 plus 2 equals the number 2 itself times 2 plus 1 divided by 2. Is that a true statement or not? So 1 plus 2 is 3. And what is 2 times 2 plus 1 over 2?
6 over 2.
6 over 2, which is also 3. So that's actually true as well. So some propositions are true always. So we could say that proposition, so we could say for all numbers n, P of n is true, except there's a little bit of a problem with even that. This is actually one of the reasons why this class is called discrete math. We have to define what we mean by what kind of a thing is n. So would this be true if n is a like an irrational number like pi? You can't find the numbers from 1 plus 2 all the way through pi because pi isn't an integer, right? So we can just say for all natural numbers, we could say. So this for all n actually needs to be qualified a little bit. What's this? So the language of math has lots of shorthand notations. One of the shorthand notation is belongs to. So remember, how many of you are at the convocation yesterday? Like so remember they said you belong to friends now? Remember that? So the symbol that means something belongs to something means that. It's that little thing like that. It means you're an element of. It's also called an element of. And natural numbers, N, they use the letter capital N for that. Natural numbers N, the symbol for natural numbers is capital N, but with an extra line drawn through the left side to make it look like it's three-dimensional, like that. So it's like N with another line written to it. So the shorthand way of writing this is to say for all N, they're elements of the natural numbers, P of N. And the word is true isn't used for something that's a logical output, because that just means for all N, and then this is the output or whatever. For all N, P of N. For all of N that are in the natural numbers. Now that looks like Greek, right? Because it is basically Greek. So, but it's very useful though, because you can express things more precisely than before when you have those kinds of notations. Now let's talk about something. Let's give this a name real quick. That symbol officially is just called for all. Because like, for what values is it true? It means for all numbers that are part of the natural numbers. But then there's a name for that though. They call it also known as the universal quantifier. So it means for all of them. The universal, oops, I left out part of a quantifier. Quantifier. So the universal quantifier is like an upside down letter A. And sometimes if I'm taking notes in a meeting and they said, well, all the people did whatever, blah, 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 I'll just use shorthand notation and I'll just write an upside down capital letter A, because that means for all. So now that you know that, you can use it in your own notes if you ever want to write all of something. Okay, well, how about they don't even say this word in the book, at least not as far as I can tell, but how about something called the existential? What does existential mean? That means having to do with existence. Existential quantifier, it's like the opposite of the universal quantifier. And it's like sort of like the element the symbol belongs to, but it points the other direction and it's square instead of curved. The existential quantifier is like this, and that means there exists. There exists. And now it does not say whether there exists one or two. It just means that there exists. So it really actually means if something exists, but you don't know how many of it exists, you don't know if there's two of them, you know that there's at least one, but there's an unknown number that exists, right? So if I said, there exists a person who is 8 feet tall. Is that a true or false statement? Well, actually, I don't really know if it's true or false, but Robert Wadlow, I believe, was 8 feet 11 inches tall. And so there is probably somebody in the world who's 8 feet tall right now, because that'd be 11 inches shorter than the tallest one was. Does anybody know who the tallest person in the world is right at this moment? So there probably is somebody who's 8 feet tall right now. That'd be pretty exciting. Yeah, probably somebody. So there exists a person who's 8 feet tall. Now let me ask you the question about this though. There exists a person who's 8 feet tall. What if I put an exclamation person after it though? Okay, so that does typically mean not. It does typically mean not. But in this case, this means there exists a unique person. Well, not person, just there exists a unique thing. So if I said there exists a unique person who is 8 feet tall or more, that would actually be false if there's more than 2 people that are 8 feet tall. But it'd be true if there's only one.
You also just say there is one. There's just one.
Well,
Or is that-
there, yeah, you could say it in words, I guess, if you wanted to say there exists just one person, but the existence operator itself doesn't specify whether there's just one or not. So you'd have to like either spell it out, or you could just say exclamation point after it. Let's see, what else could we do? Okay, let's talk about a little bit of logic again. Okay, so let's talk about logic again and negating quantifiers. So let's say you have a quantifier that says for all x, and I'm just gonna say let there be a set called S. Let S be a set of numbers, I'll say. So for all x that are in the set of numbers, I'm gonna say it's true that I'm gonna say H for hypothetical. So let H of x be an unknown proposition. So if I had the statement for all x that are in the set S, then H of x is true. So that's what that means. For all x that are in the set S, H of x is true. What's the negation of that? What is the logical negation of this statement right here, of that statement? So what's the negation of the for all something? So if I said I have folded all of my clothes, if I lied about that, what would that mean?
that is not overall.
Yes, but be a little bit more specific though. What level of, does that mean if I've not folded all of my clothes, does that mean that I haven't folded a single one? No, because I could have just folded half of them, right? So what this means, the negation of that means there exists an X in S, right? There exists, that means at least one, and we don't know how many it is, there's at least one though. There exists an X that's within that, like the clothes that I was supposed to fold. So think of the S being the set of clothes that I'm supposed to fold. And think of the X being there exists at least one clothes that I was in that set of clothes that I did not fold. So doing the not H of X like that. So the negation of that statement for all X in S, H of X is there's at least one thing in S such that it's not H of X. So like if H of X means you folded your clothes, there's at least one thing of clothes that I did not fold, right? So the negation of that is the negation of the for all is just there exists. And let's see. Let's talk about something really complicated. So how many of you know what this means right here? What does that symbol that looks like a pi mean? If you say like I equals 1 at the bottom and 3 at the top and then like I but after it, what does that stand for? So this symbol means product. And this means you find the product of all the numbers called I from 1 through 3. So that means it is 1, first of all, and then 2, and then 3. So it's equal to 6, like that. So I equals 1 to 3 of I is 1 times 2 times 3 equals 6. What if I changed it to be the product of all numbers from 1 through 4? What would that be? That would be, put a 4 at the top and be 1 times 2 times 3 times 4. That's just a quick and easy way of doing it. So 6 times 4 is 24, yeah. Now let me show you another interesting thing. What if I said I have 10, okay, so I said I have 12 total kids, so there's 11 siblings I have. What if I said that, what if I said that the statement, let's just think. What's the coolest country in the world to go to, do you think? Yeah, right. So what's the next coolest country in the world though? New Zealand. Okay, I'm gonna say like Z for New Zealand. So let ZI be the statement that the ith child of my sibling of Joseph's kid parents or whatever. I'll just say Jay's parents. So ZI is a statement, the ith, actually I could say Z parentheses out like that. So ZI is a proposition that the ith child of Jay's parents has visited New Zealand. So do you understand what that stands for? So what does the statement Z1 mean? What does the statement Z1 stand for? That means the first child of my parents visited New Zealand, which would be Elizabeth. What does Z2 mean? That means the second child of my parents would have visited New Zealand, which would be my brother Matthew. So basically the statement ZI means that is defined as the ith child of my parents has visited New Zealand. How would I write that none of the children of my parents have visited New Zealand? How would I write that? So we're going to use a notation similar to this product notation. We're going to use the symbol for and. What's the symbol for and? So if you want to say one thing and another and another and another and another and another and another, and there's lots of things to say, this is a symbol for and, right? What?
Oh, say up arrow.
Yeah, so like an up arrow, right? So we're going to use a symbol for and we're just going to start with the youngest child, or the oldest child, I guess, child number 1. I equals 1 through 12. And then we're just going to say not ZI. That symbol right there means it puts together all of those statements together with a not. So what does that mean? This equals not Z1, and then it puts the symbol and between them. Not Z2, it means not Z3 either. And it keeps doing that all the way until it gets to saying and also not Z4. Not Z4, sorry, it's not Z12. So if you say it's not true that you have Z1, not true that you have Z2, it's not true you have Z3, it's not true that you have anything all the way up to Z12. There's a lot of and signs between all those different things, right? So instead of writing them out the long way, you can just put one single and sign in front, and then to say I equals 1 through 12, and then to say what you want to say after it, like that. So the symbol that you want to apply to a big group of things, you can just put that first, and then you can write which one to start with and which one to end with, below it and above it. So what do you think this would stand for? If I just said plus, and then I equals 1 through 10 of I. If I use that same type of process. I equals 1 through 10 of I, that would just mean 1, and then put the symbol plus, and then I let I equal 2, I equal 3, etc., all the way through 10. Just add them all together. By the way, this would actually make a little bit more sense if they did it this way. They don't normally use a plus symbol though. To add things from 1 through 10, they don't usually just say plus. They use this symbol right there for some reason. That's one that you learn in algebra. if you wanted to add i's from 1 through 10, you'd do it like that. I don't know why that they use this symbol instead of a plus sign, but in logic, it's a little bit more logical. They just use the sign that they actually wanted to put between things, and then they write the things at the bottom and the top.
Why I said, oh, hey, that works.
Yeah, they probably just drew a squiggly line.
Get the energy, all right.
Yeah, that would mean the same thing, although people would really look at you funny if you tried to do it like that, even though it would make logical sense. The one at the top is not really how people do it, because people are used to the tradition of doing it well, it's not really the wrong way. People are used to doing it with the bottom symbol instead of a plus sign.
Is that how you want us to do it?
Yeah, I guess I'd rather just have you keep on doing it the traditional way like that.
Yes.
Okay, what if you wanted to? Let's just see. Wow, there's a lot of things. Okay, so let me have you translate this statement into English for me. Just out loud with your verbal words. Okay, so what does this mean? And so imagine that the set is all real numbers, which a lot of the exercises in this book just assume that the quantifiers are referring to regular real numbers. So they don't always say like this represents natural numbers, they just assume it's real numbers. So for all x, there exists y, parentheses, x less than y. What does that mean? So I basically said it already. So what that means is for all real numbers x, there exists y such that x is less than y. Is that true or is that false? So first of all, it means for all real numbers, there exists a y such that x is less than y. So think of a real number. Just give me any real number you want to. Well, just think of one. One, yeah. So think of the real number 1. Does there exist a real number? So that's x. Now think of y. Does there exist any y value such that 1 is less than the value of y?
0.
Well, but we're trying to find one that exists. So the 1 is less than it though. So how about 2? So for no matter what number you pick, like you pick 1, then there would be a 2, right? Such that 1 is less than 2, right? If you picked 100, there would exist a number like 101, which is so that 100 is less than 101, right? So it's true that for all real numbers, there exists at least one other number that's bigger than it, right? So that's true. Let me reverse that and just see, can you reverse quantifiers or not? Is it fair to say that there exists x such that for all y, x is less than y? Is that true?
Yeah.
Well, is there a real number so that for all real numbers that x is always lower than all real numbers? No, because no matter what number you pick, once you've picked it, even if you picked a small number, it's not true that all numbers in the world, because this could be the same number, it could be less, it could be more, it could be anything. It's not true that there's one number that exists so that all numbers are bigger than that one number. So for example, let's just say that I picked a number. Let's say I picked a number. And I don't know what the number is, right? So that equals x. Well, once x is picked, though, it's only one certain thing. I could pick y equals to a number that's less than x, right? Because there's always a number less than it. So if I picked y to be a number less than it, then it would be false that x is less than y because y is actually less than x, right? So that statement is actually false. This statement is false because it's not true that there exists a number so that every real number is bigger than that number. But this statement is true though, right? So you can't just switch things around any way that you want them to be. Let's just see. Okay, well, so I've already sent you some homework for this week. And next time that we come back on Monday, I'm going to talk about some arguments for propositional logic. So this is not the kind of arguments like you get mad at somebody and argue with them, but it's just like how to logically work together through a little bit of logic using propositions and maybe coming to a conclusion from them. So let's see, we have 4 minutes left. Does anybody have any questions about anything at all? Yes.
So in the middle of the homework assignment, you're just doing the questions that you said do, and then don't do the.
Yeah, don't do the other ones. Yeah, don't do the other ones. Yep.
That's due tonight, right?
That is due. I probably did say tonight. Is that what it says right now?
Yeah.
Okay, so I guess, do you think you can get it done by tonight? It's only like 4 questions, I think. That's only a few. Well, how many is it? This is like it's like two truth tables and one.
It's technically 4 problems, but like a lot of them have like A, B, C, D.
Oh, it is, okay.
Yeah.
Well, didn't I just assign like part E or something on?
A couple of them you just assign one.
Okay, so I guess I could give you until, how about if I give you until, would you rather have Saturday or Sunday to do it until? Sunday, okay. So I can change the due date to be Sunday.
Yeah, there's 13 of them.
Okay, so the homework, the new homework, not the old one, but the new one is gonna be due on Sunday. So good job. And have a good weekend, everybody.
Is this not the homework where we had to go through like 280, 480, 880, 1080?
So let me look, bro. You might have actually gotten ahead of us. Let me, hold on, let me, real quick.